Thank you very much, Chairman. So this is a continued presentation from the keynote, in a way, about what we have been doing and what we plan to do in the phase resolved modeling domain with RIF 3D. As the professor just mentioned, in the following presentation, there's no water level maxima, so water level the same, constant. But nonetheless, we'll see a lot of physics still about what's happening in more detail around the Baltic harbors and Baltic shores. So first, we need to look at the Baltic, or like Eastern Baltic region, and what are the characteristics that we're looking at before we dive on into the numerical modeling. So first is that we see actually quite large water bodies. As you can see, I have a laser, is the Gulf of Finland is very elongated water body. So it's quite narrow relatively, north-south wise, but it's quite long, east and western wise. So that means actually at least along the east and western direction, we expect quite long fetch. It allows the wind to blow over the surface and generate quite large local wind waves. Even though we're not exposed to the North Atlantic, we probably don't have as huge swells, but we get very long fetch in the west-east direction. So we can expect high waves, in fact, when it's not covered by ice, that is. And also, we look at the water depth. You can't read the numbers, but for most of it, you have a water depth contour near the deepest part at about 50 meters. And only when you reach to the west, close to Gotland, you have 100-meter water depth. So it's in generally about 50-meter water depth. And that's a water depth that is kind of intermediate, but it depends on the wave condition as well. Because when we talk about water depth, it's never only about the absolute depth, but about a relationship between the water depths to wavelength. And since we can expect quite a lot of locally wind-generated waves, so that means we have a large range of frequencies of waves. So it could range from deep water to intermediate water depth. That's the kind of from simulation point of view, what we expect. So that's what means that using pure two-dimensional shallow water model for Baltic region might not be the most appropriate solution. So we need to go a bit deeper. And also, when we look at the coastlines around the Baltic, that's the part I really love about it, is that you have so many beaches. I need to come back in summer and enjoy the beach, because in Norway it's only rocky coast. Here we have a lot of sandy beach. We look at, for example, along the Gulf of Finland, and look at two locations. The harbor at Nassere. You can see the sediment deposition to the north side of the harbor, and a long beach, and you can see the subsea dunes. Also to the east, close to Narva Juisu, if I pronounce it correctly, you can also see a very long stretch of beach with a river entry right in the middle. Similarly, if we move to the Gulf of Riga, also look at two locations at the harbor at Runo. Again, it's a harbor actually in the middle of a very sandy beach as well. And when we look at, not exactly at the Pärnu harbor, but we look at the Vagrena beach to the north part of the Pärnu Bay, you can also see the formation of subsea dunes. So it's a very sandy beach, which means that sediment transport is a very important aspect in all the simulations. So that's also why, following the keynote, why Professor Hans presented the new model, NH flow, to be able to represent the coastal swirlstone dynamics and to be able to include viscosity and turbulence for sediment transport in the future. So you have already seen this slide. We develop our own kind of, basically it's developed by Hansbis and the group at NTNU in Norway. It's open source model for wave hydrodynamics. And yeah, you can actually visit the website and download and give a play. So at the moment, we have 4 different types of models. The CFD model to the left corner, that's very high resolution. So it's not really suitable for such a large domain that we are looking at. The shallow water model to the right corner is S-flow. As I mentioned, in Baltic region, it's actually quite intermediate to deep water condition. So we are not using that model for the Baltic. Instead, we focus on these two models, the fully nonlinear potential flow models. That is very good for wave propagation over a large area with drastic water depth variations. And also the NH flow that has similar properties as FMPF, but in addition, it can also include viscosity, source zone dynamics, and turbulence in the future. So the videos are playing perfect. Oh, is it? Wait. So I just give you an impression of what these two models might look like in real time. So first, the governing equations are different, as you've seen in the keynote. Second, so FMPF is very good at wave propagation and transformation from deep to shallow water over very drastic water depth change. But NH flow, it will be able to, you see the video, look at the coastline area, the waves moving up and down. Like the wave run up above the mean water level and run down. This process in the source zone area is what really makes the NH flow very suitable for the Baltic region, because we need to look at the coastal morphology. So what we have been doing is we used FMPF model, the wave propagation model, for the wave analysis. So wave analysis alone with wave transformations, but not any coastal source zone dynamics. So especially we look at the effects of the breakwaters. As an example, we look at the wave scenario around Nassau harbor that I presented in IHR last year. And in the keynote, you have seen some of the simulations, so I will focus on the Runo harbor. At the Runo, that is old harbor layout. As you can see, we have two breakwaters surrounding the harbor, and then we have an intermediate breakwater around in the middle of the harbor. That is where the ferry terminal is located. And we used Junttila spectrum that took the measurement from our Estonian partners that I took the largest significant wave height and the longest peak period. So it's not the steepest wave, but it represents the largest wave height and longest peak period. And we applied a Mitsuyasu type of directional spreading because it might be wind-generated wave. So it's but I use a very large, so shape factor 28. So it's very narrowly spreading. See, it's almost like swell. And it has about 2 million cells in total in this simulation, and this domain is about 1.25 kilometers in each direction. I run this model for 3.5 hours because in industry standard, quite often we need a 3-hour time series to produce statistical values. So then I give an extra half an hour to let the wave propagate and stabilize. And that took 2.5 hours for us to actually calculate it. At a local machine with 128 cores. So it's actually faster than real time. And with the flexibility of the numerical wave model, we can look at the wave propagations from different directions to investigate, okay, what could possibly be the most dangerous scenarios for the harbor, for example. And then we can also compare the new harbor layout to the right-hand side of the images. Oh, so all of those are with new harbor layout, and the previous slide is old harbor layout. And then we can look at the wave height changes at all wave gauges, 1 to 6 from offshore to inner harbor. And all the dashed lines in the right-hand side upper image, they are from the old harbor layout. All the solid lines are from the new harbor layout. And you can see wave height has been reduced significantly, especially along the navigation channel for the ferry. But also you can see, if you look at the green line, there's a peak at wave gauge 4 that has increased wave height for the wave direction from the southeast, which means that it's the wave direction here. So the wave is coming straight into the harbor, aligned with the navigation channel. So that creates the most dangerous scenario. But also we can look at how the spectrum or how the wave energy is distributing over different frequencies. You can see in the old harbor, shown as dashed line, In the inner harbor area, you have 1, 2, 3, 4 peaks, or almost 5 peaks. So due to the wave interaction and transformation, you have like a 5-mode wave condition in the old harbor layout. But in the new harbor layout, in the inner harbor, you have only 2 predominant peaks. So that actually makes it's easier to design your infrastructure, so we'll consider only 2 primary modes instead of 5 primary modes. So that's one of the studies that we've been doing with FMPF. But with NH flow, we can also reproduce very similar results. That's with NH flow now. And it's also 3D model, so you actually can look at the cross-sections on how the waves are propagating towards the coast. But also, if you look at the coastline, you see a bit whited areas that indicates the wave run up above the still water level. So we can actually look at the swashstone dynamics. This might look a bit weird because I stretched vertically for 20 with a factor of 20 just for visualization. So it's not really the waves are splashing up so high. For another example I would like to show is at also Narva Jusu. Because again, that's a very good example for very sandy, long sandy beach. And also there's a river entry, so you would have additional current and discharge into the water body. So this is the simulation video clip with NH flow this time. And that's the Narva River coming into the coast, and we have also, again, short-crested wave propagating towards the coast. Because of the natural geometry of the coast, so the waves coming straight from west, but actually it's inclined wave, so the wave approach the shore at an inclined angle. And if you also zoom in a little bit more detail to the coast, you can see how the wave propagates. And if you really focus your eyes on the coastline, you can see the waves run up and run down. Basically, the coastline geometry changes over time because of wave run up and run down. That's also, again, the difference between NH flow and FMPF, because in a potential flow model, the coastline is fixed. But in this model, the coastline is not fixed, so we can have the coastline, coast swashstone dynamics. And you have seen this picture before, but I want to explain a little bit more. It's a very interesting picture when we look at the cross-section, because as we also heard from yesterday, there are longshore sediment transport, there are also cross-shore sediment transport. So now we look at the cross-shore section from relatively offshore towards the harbor. There are many interesting details here you can see, not all relevant to the sediment transport, but if you look at this group of waves, that reminds me of how the three sister freak wave would take place. The freak waves can take place in offshore area, in coastal area. It does not need to be like 30-meter tall waves, but it just need to be way much higher than the surrounding neighboring waves. So in this case, the definition basically is like if you have a wave height over twice that of the neighboring significant wave height, then you have a freak wave. And this pattern really reminds me of the freak wave pattern. I don't know what it is, but due to this bottom bathymetry variations and wave direction, you could actually have a locally focused waves. That's very interesting to observe in the simulation. Another interesting thing is that you see a belt of higher waves, it's more red when the waves approach the shore, which indicates the surf zone. So a lot of waves will break already at this location, and after this surge of high waves, the wave height become reduced. That's because of the dissipation of wave energy after the breaking. And the waves will run up to the shore, and then you reach the swash zone. So that's just a very interesting detail to look at. And so that's more like what we can use it for cross-shore information, because what I showed was x direction velocity, and you can use x direction velocity to calculate the bottom shear stress, for example, once we include the turbulence model, and then you can calculate cross-shore sediment transport. But then also here, I'm looking at the velocity in the y direction. Now you look at the color scheme. Because the waves are approaching to the shore in oblique angle, and also due to the wave transformations, due to the coastline geometry and bottom bathymetry, we do observe quite high lateral y direction velocity close to the shore. So that might indicate wave-driven current, longshore current, that is relevant to what we heard yesterday, wave-driven longshore currents along the Baltic region. And last, about time, a quick summary, why we have an inch flow, because it can have all the wave transformations from deep to shallow water, it can represent source zone. And in future, what we are going to implement is also river currents and sediment transport, including turbulence. So this is also the Narva river mouth into Baltic Sea, and that's the current day status. And I think they do have the plan to build a new breakwater. So you can have a look at the video. Credit to our Estonian partner, Rin Monicus. He shared this video. So this breakwater is actually kind of abandoned nowadays. It's not fully in function at the river mouth, and there will be a new breakwater. So we hope to also maybe can contribute in this process, because it's not only about protecting the shipping lanes, but also how do you intercept or change the sediment transport patterns along the coast. Thank you very much.
Thank you very much for this very thorough investigation of the harbours. So we have certainly some interesting questions here. At least I have in the beginning, if you compare this Baltic harbours with some of these Norwegian harbours, you certainly will find some differences. Maybe in Norway it's much deeper, or what kind of channels you have in the harbours. So can you explain if the Baltic harbours are somehow different or not?
Thank you very much. Yeah. That's a very good question. I think there are two probably three main differences between the Norwegian harbour and the Baltic harbour. In the Norwegian area, indeed, because of the existence of fjords and a lot of harbours along the fjords, so the water depth changes. It's more drastic. You can have so almost 45-degree slope, subsea slope outside the harbour. You move out 500 meters, then you already have 500 meters water depth. So that's a very drastic change. But also many Norwegian harbour are more also prone to large swells from the North Sea. Mm-hmm. So you have very long waves that can penetrate deep into the harbour. But the Norwegian coast is very rocky, mostly. So sediment transport is not that predominant. But in the Baltic area, I think that's very important. So the harbor design has to think so much on dredging process, not only how to protect the harbor from waves, but how to protect from sediments and morphology changes. So that's an additional challenge, I think.
And what about the lack of tides in the Baltic Sea compared to Norway?
Yeah, that's also very interesting. Also followed the last presentation. I think that's a relatively new domain for me, for research-wise, also to look at tides, also storm surges, and different mean water level variations. That I think I have to do a bit more homework on that one to answer this question.
Okay, thanks. Okay, do we have some questions from the audience? I cannot see now any hands rising. People start to be tired, I think, after the party last night. But thank you very much for this interesting presentation.